no inverse response. The higher the higher order transfer function. But what we get from our step changes are the open loop transfer functions, the transfer functions that tell the story when the controller is set on manual. So let me remind you. So when the controller is on manual, we have Laplace transform of the output deviation equals the Planck transfer function and the Laplace transform of the manipulated input. And for each disturbance, an open loop disturbance transfer function times the Laplace transform of the disturbance deviation. And I think I was thinking I was driving, and I think that I will name this M to denote that this is what tells the story when we have the controller on manual. Controller on automatic M still holds, but M doesn't tell the entire story. In addition, you have now U prime bar. Instead of being an input that I, the operator, is giving, depends on the set point, depends on the error actually, and the error is a distance between set point and measure. So if we take everything into account as we saw last time, we get the closed loop transfer functions, and now the inputs, instead of being manipulated into the disturbances, they are set point, desired value in disturbances. So set point deviation, and we'll have also disturbances continue being inputs, but the transfer functions are going to be different. So I'm putting a CL here and a CL on top to indicate a closed loop. And let me call this equation A, since that's the story for automatic. Okay? How are we doing? Crystal clear? Okay. And we saw also, we derived the relationship between the closed loop transfer functions and the open loop transfer functions and the feedback controller transfer function. The feedback controller in the Laplace domain is where, of course, E bar this is the most common form, although you can have a more generalized version of it that it's something times y prime bar set point plus something times y prime bar. This is the most usual form, although when I show you the more controller, one is an example of an industrial controller, you will see it's not strictly that, it's that, assuming that your step changes, that your set point changes are piecewise constant, which is usually the case. And so we found the relationship between the closed loop transfer functions, both for the set point and the disturbances, and the open loop transfer functions, and what we are designing. And what we are designing as engineers is the controller and the controller transfer function, GC. And GCL of S was dU of S, dC of S, over 1 plus GU of S, dC C of x. And all disturbance transfer functions, closed loop transfer functions, and the open loop disturbance transfer functions divided by 1 plus GU of S, GC of S. And we're designing the GC of S. One important thing to observe is that all closed loop transfer functions have the same denominator, 1 plus GU GC. So, and one other thing, this picture is associated with the block diagram that we're using in the class. The difference between set point and measurement is the error. GC times the error is U prime bar. And the sum of GU times U prime bar plus for every disturbance, open loop transfer function GD1 for D1, and so on, GDR for the last disturbance. Y prime bar is GU prime bar plus sum of GDI DI prime bar. In other words, this is equation N. This part of the block diagram is equation N, what we have on right. And this Y prime bar is the same that is returned to calculate the error. That's why we have a closed loop. And this part, notice the inputs, arrows coming from outside, those lines. This is what is represented by equation A. Clear? So that's where we are right now. Some other observations. Remember, we learned a lot of things about system dynamics given transfer function. For example, stability requires that all poles, denominator roots of the transfer function, have negative real part. Open loop stability requires that all the poles of GU and GDI have negative real part. Closed loop stability requires that all the poles of the closed loop transfer functions have negative real part. Okay? However, I want to point out something. What is the U I've been talking about here? It's what comes out of the controller device. Okay? It's the signal that leaves the controller device. What is Y? The signal that enters the controller device. Okay? As you saw in the actual control system of the Unidot lab, has several components. And those components have inputs and outputs. And in a linear model, whenever you have an input-output relationship, you have a transfer function between. Let me remind you of what was the architecture of a typical control loop we saw in the Unidops lab. So we had typical control loop with device. So we have the set point, the difference from the measurement is the error, and this goes to the controller. I will drop putting of S, all transfer functions are of S. So what comes out is the output of the controller. Where does the electronic output of the controller go? It's an electronic signal. Do you remember where it went? Hold it.
Airflow rate to open and close the valve?
Not quite. You have an electrical signal. You mentioned valve. What does the typical valve have to open it or close it?
The flow rate out?
How is the typical control valve we saw in the Unidops lab opening or closing? Or what does it get to open and close?
The output. The output?
Thomas? Absolutely. It gets air. So we will have here the current to air converter. So we would have a transfer function G, let's say, after the name, C to A. That goes to the control valve, right? That goes to the control valve. And the control valve would change, for example, a flow rate, okay, which is the actual physical variable that we are manipulating. So the actual physical variable that we're manipulating is typically some flow rate. It can be something else. For example, if I have a heating strip, you can directly change the current to the heating strip. Okay, it's not always the case. I'm just having a typical, a common control loop. So here, what comes out is, so here would be air signal. So let's call it A prime bar for air signal. Here is, let's say, U physical. Okay? And that's what goes to the process. And the process will have some transfer function.
Is A for current?
Hmm?
A is for current?
No, but
Air, oh,
wouldn't make any sense
yeah.
with an A for something that starts with a C.
Oops.
Okay. So here is the actual process. So let's say the transfer function between the physical input, the GP here, and processing.
By U physical, you mean like a fluid or something? Sorry.
The flow rate, the
Okay.
actual flow rate. That's the signal that's being affected, right? temperature, some state variable. That changes some state variable. So let's put here xi prime bar, which is the measured state variable. That will now go to a measuring device. And that's the signal that is being returned. And what about disturbances? Well, disturbances can be entering directly the process, could be entering the measuring device, could be affected by disturbance. You could have a disturbance affecting the air pressure coming out of the air to pressure, current to air converter. So there's a possibility you have a disturbance entering here. Okay? So disturbances can enter at different places. Okay? If the pressure of the plant drops some, that will affect the current to air out, because that depends on a certain pressure of air coming in. If the process, a lot of things can change. Anything that's coming upstream will affect it. Measuring devices, probably rarer, but well, not so rare actually now that I think of it. I had a situation like that in my research many years ago. We're doing some experiments in which we're measuring luminescence. And noticed that whenever the air handlers were going on, the measuring signal was changing. It was affected by the draw of the current by the air handlers. So there's several places you can have disturbances, and each one of them you can would have probably a different transfer function. So you could have here a GD1, but actually let me do it simple. G the real 1, prime bar, G the real 2, so that's the real picture. However, that real picture can always be recast to the picture we have used in class. And what do you get when you do an experiment? The output of an experimental step change is the picture we've been doing in class. Okay? Understand that I use the picture above because that's the data you actually get from experimental step change. Now, if you're doing a mathematical model, you need to model all of those things. Okay? And actually, so let's put here figure 1. Let's put this figure 2. Figure 2 can always be recast as figure 1. And the relationship between the transfer functions in figure 2 and the transfer functions in figure 1 is that GU